We are going to use the definite integral to find the area under a curve. Let's get an idea of what's going to happen here. I'll draw a curve. Maybe it looks like this. Just some curve, f of x. And what we want to do is maybe from the left end point, call it A, to this right end point here, call it B. What we want to do is find the area of this region right here. Turns out that the definite integral also measures exactly the area under this curve, and it just put up the relationship between area and the definite integral. So here's what this comes to be. The area and the definite integral. All right, if f of x is a continuous function like this one over here, right, we have a continuous function. Non-negative means it lies completely above the x-axis. So we've got a continuous function, non-negative, on the interval a to b, so that's us. Like, look what we have over here. We have a continuous function, it's non-negative, that means the curve lies completely above the x-axis, and we're going from the interval, on this interval, from a to b, then we're going to define the area, right? So the area in square units, bounded by the function, the area bounded by the function, the vertical lines, x equals a and x equals b, and the x-axis is precisely this definite integral right here. So the area is defined to be the definite integral from a to b of f of x dx. So before we actually start doing some of these, let's see where this comes from. Why is this true? Why is the area equal to that definite integral? Let's start by approximating the area under the curve. So we'll work our way up to the exact area, but first of all, let's approximating the area. So let's start here. So I'll draw a picture, again, x and y. Okay, and then here's maybe a curve. Here's f of x. And maybe we're going to go from A to B. And what we're going to do is break this interval up into 4 rectangles. So I'm going to approximate this using 4 rectangles. Now I just picked 4 because it's a small number to work with. I don't have too many computations to make, but I could use 2, 4, 6, 8, whatever I like. So I'm going to call that n. That's going to be the number of rectangles. N will be the number of rectangles that we use in our approximation. Now, if I'm going to use 4 rectangles, I'm just going to make these lengths here the same. I'll make them all the same. So I'm going to have a rectangle of this length right here, then one of this length, and this length, and all those lengths are going to be the same. In fact, here's how I'm going to get that. I'm going to call this length right here, I'm going to call it delta x. Now this is the Greek letter delta, and in mathematics it means change. So what we have going on here is a small change in x. Right? X is going from here to here, so x is changing in value. So I'm going to call that delta x, and that's going to be the length of the base of this rectangle. So we'll have 4 rectangles, all having the base of the same length. Now the area of a rectangle is, we have a formula for this, right? Length times width, or if you like, base times height. So this area is going to be the base, which is delta x. So the area of a single rectangle is the base times the height, but the height, what is the height? That's going to be f of x. Let's look at how I'm getting that. So I'm going to maybe start here, and this rectangle, I'll take all the way up to here and then bring it over here like this. So if I draw that, it's going to look like this. I'll start here, I'll come up to the function, and then I'll come over here, down here. So I've got a rectangle with this base, and what height? The height is the length up to that function value. So it's delta x, the base, times the height, which is f of x, right? Delta x, f of x. But what I want to do, of course, is I want to just I get the area of this rectangle, and then this one, and this one. So I'm coming off the left-hand endpoint. So here's my first one. Now come off that endpoint again. So there's the first one. I'm going to come off of this one. I'm going to come up here and bring it over, and that'll be my second rectangle. Then my third one I'll get by coming off here and over here. That's my third rectangle. Then I'm going to come off here and bring it over here. There's my fourth rectangle. So now I've got 1, 2, 3, 4 rectangles, and I can get the area of each one. So just some notation so I can write this out. I'm going to call this left endpoint x sub 0. That's going to be x sub 0. This one's going to be x sub 1. This is x sub 2. That's x sub 3. And this one here is x sub 4. So now my area is going to be approximately, say, the base delta x times f of x sub 0. Make sense? I'm going to put x sub 0 in and compute, and that'll take me up to here. So whatever this is, whatever that value is, that's the height of that rectangle. Then I'm going to add this one here. Now this is coming off of x1, but it's still got the same base. So this is going to be, let me add that in, plus delta x times f of x1. So let's get the areas of these other rectangles. I've got the first two. This one comes off x sub 2, right? So this is going to be our delta x is the same, but our height is going to be f of x sub 2. So we're going to add in delta x times f of x sub 2. And then the last one, we're going to add in delta x times f of x sub 3. Let's just check that. The last one, x sub 3, that's this one. So I'm coming off these left-hand endpoints. If I come off the very first one, x sub 0, I get this rectangle. X sub 1 generates this rectangle, x sub 2 this rectangle, and x sub 3 this rectangle. So all we have to do now is find delta x and all these particular values. But what I'm going to do here is this. The area is going to be approximately, I'm going to factor out that delta x. And if I factor out that delta x, I'm left with this. F of x sub 0 plus f of x sub 1 plus f of x sub 2 plus f of x sub 3. We have a name for this sum right here. This is called a Riemann sum after Bernhard Riemann, who developed it. So because this is a sum, instead of calling this the approximate area, what I'm going to write now is this. I'm going to call it S sub n, and the S stands for sum. The n means using n number of rectangles. Like in this one, there was 1, 2, 3, 4 rectangles. So this particular one would be S sub 4. But in general, things are going to look like this. S sub n will be delta x times f of x naught plus f of x1 plus dot 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 plus f of x sub n. Does that make sense? So I'm going to take the sum using n rectangles. So I'll get the delta x, right? That's the length of the base, times the height of the first rectangle plus the height of the second rectangle plus dot 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 plus the height of the very last rectangle. So I've got n rectangles in here altogether. Now this is the Riemann sum. And if you look back to our picture, you can see that it gives us an approximation to the area, right? It's going to be an overestimate right here. You know, I've got more area in here than I do in the curve. There's more areas in these rectangles than is actually under this curve here. But I do get an approximation. Now, what if we did this? What if instead of 4 rectangles, we put in more, right? So here's my curve, f of x. I go from A to B, and then what I do is instead of putting in 4. Now I'm going to put in, say, 8. So I put in 8 rectangles. So now things look like this, right? Here's the first rectangle. Here's the second one, the third one, the fourth one, the fifth, sixth, 7, and 8. Now if you compare these two, see I've got a lot of extra area here that really doesn't belong under the curve. Whereas over here, that excess area is diminished, right? It's smaller. I've got a better approximation over here. So in this case, we just took n equals to 8, and we got a better approximation. What we're saying is this. Well, okay, then what if we did this? What if n was equal to 80, or n was equal to 800, or 8,000, or n was equal to, say, 80 million? So what's happening now as n gets bigger, as n approaches infinity, right, n goes to infinity, that Riemann sum is approaching the actual area of the curve. You can see that here, right? Look back over here at this lower left one. I only have 4 rectangles, and the area of those rectangles is bigger probably than the area under that curve. But then when I increase the number of rectangles, that area of those rectangles is more closely approximating the actual area. And if in here we were to put 80 million rectangles, we'd be very close. But if I let n go to infinity, right, put in like close to infinitely many rectangles, I'm going to get the exact area. So here's where we are. If we take the limit of these sums, okay, I'm going to take the limit of these sums as n goes to infinity. Right now, what was that sum? That sum was this right up here. I'll rewrite it. So if I take the limit as n goes to infinity, it's going to look like this. And I'm going to write it here. It's going to be the limit as n goes to infinity of s of n was that delta x times all those heights, f of x sub naught, f of x sub 1 plus dot 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 plus f of x sub n. But I'm going to give another notation for this sum. Here's what I'm going to use. What I'm doing is I'm adding up. So I'm going to use the Greek letter sigma. Now sigma starts with an S. So does the word sum. And I'm going to add up what? F of x's. Now I'm going to call this x sub I. That's called an index. And the I is just any one of these numbers. 0, 1, 2, 3, whatever. As I goes from 1 to n. So what I'm looking at now is I want the limit as n goes to infinity of delta x times the sum of these f of x's. But now, keep in mind what these are. This is the base times all those heights, right? This is the sum of the areas of those rectangles. But if I put in infinitely many rectangles, I'm now at the exact area. So I'm going to say that the exact area is the limit as n goes to infinity of delta x times the sigma as I equals 1 to n of f of x sub I. Now, that's actually the definition of the area, but it turns out now, luckily for us, that this right here is exactly the definite integral. So that limit is the definite integral from a to b of f of x dx. And when you look closely in here, what you'll see here is the dx. Now the dx, that's the delta x in a sense. Delta x and dx are related, but dx is an infinitesimally small change in x. This is just a measurable change in x. This is infinitesimally small. So as delta x becomes really small toward infinitely small, we replace that with dx. And f of x, well, f of x is just the height of those rectangles. So it's the base times the height, add them all up. And what you might even think of is that this integral sign right here, that integral sign, that's related to this summation sign. And you can almost think as you're computing these things, you start off with a nice sigma, then the next time you write it you get this, the next time you write it here, and now you're at the integral sign. So let's just put this back up here. So if f is a continuous non-negative function, right, and that's what we drew, continuous, you know what that is. Non-negative means the function is completely above the x-axis on this interval, then the area between the x-axis and that curve and the lines x equals a and b is given by this function right here. There we go.